j, k, and m be positive constants, which of the following is equivalent to 1/3 of log base 5 k plus log base 5m minus log base 5j? So as you can tell, this equation is pretty spread out, which means we're going to probably have to condense it to make it more small. So the first thing that you can notice over here is that there's 1/3 on the outside of the parentheses of log base 5k plus log base 5m. And usually some of the properties with logarithms when it comes to combining them with things like this comes in a formula like this. So m log base a. When you have something like this, you're gonna have to move the m as a power to a. So it'd look like log a to the power of m, which is the same thing we're gonna have to do over here. So therefore, when you have 1/3 log base 5k plus log base 5m minus log base 5j. I'm just going to write over here, that way it's easier to be more spread out. We're going to put the 1/3 over here and the 1/3 over there with the log base 5k and log base 5m because it's being distributed on both logs. So that means it's going to look like log base 5k to the power of 1/3 plus log base 5m to the power of 1/3 minus log base 5j. So as you can tell, this looks a lot smaller, looks more clean, but with 1/3, when you have to something to the power of 1/3, it's also saying the cube root of something. So another way to say this is log base 5k, but the cube root of k, okay? And then same thing over here, log base 5 cube root of m, and then minus log, sorry, I'm gonna make that a little more legible, log base 5j. So it looks more clean than how it originally was. But another thing that you can do with logarithms is you can either combine them if they're being added or subtracted. So for example, if you have something like log a plus log b, you would transform that into log ab. These two would be multiplied. Or if you have something like log a minus log b, then that would look more like log a over b. Therefore, it'd be divided. So now a property that we can use right now is the log a plus log ab, which turns it to log ab. So we can use this one, log base 5 cube root of k, and log base of 5 cube root of m. We can combine those two into log base 5 cube root of k times cube root of m. And then you have the minus log 5j. Now now it's log base 5, 3 cube root k, cube root m minus log base of 5j. The next property we will be using is log base a minus log b, which transforms into log a over b. So we'll be putting the cube root k, cube root m over j. So this will look more like log base of 5, 3k, sorry, I'm gonna put the parentheses, cube root m. Again, we're gonna put this one over j. And then that is your answer. The exponential function f is defined by f of x equals ab to the power of x, where b is a positive constant. The table gives values of f of x at selected values of x. Which of the following statements is true? So just in case you need to see the statement again. And here are your options. F demonstrates exponential decay because a is less than 0 and 0 is less than b and less than 1. F demonstrates exponential decay because a is less than 0 and b is greater than 1. F demonstrates exponential growth because a is less than 0 and 0 is less than b, which is less than 1. And F demonstrates exponential growth because a is less than 0 and b is greater than 1. So the first thing we have to determine is whether this graph will show exponential decay or exponential growth. So let's use a graph over here. Now, one of the first things I notice is that these numbers are negative, and maybe you'll assume, okay, if it's negative, then it will be exponential decay. Not true. So let's start a couple. So at 0, you can tell it's at negative half. Let's put negative 1 over here, okay? This will be at negative half. But then 1 is at negative 1 over 4. So if it's at negative 1 over 4, it'll be over here. And then 2 is at negative 1/8. So this will be over here. And then 3 is at negative 1 over 16. And then 4 is at negative 1 over 32. So even though these are negative, you can tell this is going up. It's gradually going up. Therefore, it is exponential growth, which cancels out A and B. Now, another thing you notice is that C and D both say that, okay, A is less than 0. So we're going to have to ignore that. And then we're going to have to go on to B. Would B be in between 0 and 1, or would B be greater than 1? Another thing I notice about these numbers is that not only are they negative for the outputs, but they are also fractions. But the bottom parts of the fractions, the denominators, they're getting bigger and bigger and bigger. And so I would have to assume that B is in between 0 and 1, which means it's a fraction. So if B is a fraction, usually when you put a fraction to the power of something and it's in between 0 and 1, the denominator is less than the denominator. So it'd be something like 1/2, okay? If you keep putting it to, let's say if you have 1/2 and you put it to the power of something. Let's say you put it to the power of 2. Then it would be 1 over 4. So the bottom number is getting bigger. And then if you're to square it again, 1 over 16, and then so forth and so on. So you can tell that the denominator is gradually getting bigger and bigger and bigger because it keeps getting squared because it keeps going to the power of something, and the power of something is getting bigger and bigger. So not only is it exponential growth, but A is less than 0 because these are negatives, and B is in between 0 and 1 because these are fractions, and these fractions, the denominators of the fractions are getting bigger and bigger. So this would be C. In a certain simulation, the population of a bacteria colony can be modeled using a geometric sequence, where the first day of the simulation is day 1. The population on day 4 was 4,000 bacteria, and the population on day 8 was 49,000 bacteria. What was the population of the colony on day 6 based on the simulation? The first thing that we can take away from this problem is that it's a geometric sequence, which means we're going to most likely use a geometric sequence formula in order to find day 6. Two other things that we can take from this are day 4 and day 8. So on day 4, there was 4,000 bacteria. On day 8, there was 49,000 bacteria. How do we find day 6? The first thing that we're going to have to do is put the inputs and outputs from day 4 and day 8 into the geometric sequence formula, which is n equals r, and then to the power of n minus 1. So the first one is day 8. We're going to do day 8 first. So day 8 was a 8, which tells us the day. which is also equivalent to 49,000 bacteria, which says so in the problem. And then you have AO, which we haven't found yet. And then you have R, again, haven't found yet. And because this is 8, n equals 8, we're going to do 8 minus 1, which is then 7. So now the first part is done. The next thing we're going to do is A4. And then you're going to put it to as 4,000 equals AOR. And because n equals 4, you're going to do 4 minus 1, which is then 3. So now we have these two equations, but how do we find day 6? That's the next thing that we're going to get into. So we're going to divide the two. We're going to divide day 8 and day 4, or A8 and A4. So let's put this into our calculators, which is what you're going to need for this problem. What is 49,000 divided by 4,000? Let's check it. You get 12.25. So you put 12.25 over here. Now how do we figure out the rest? Now because there's only 1 and 1a over here, they cancel each other out. As for the r's, r to the power 7 is on the top and r to the power 3 is on the bottom. When you have when you have numbers or variables that are the same and they have different powers and you're dividing them, you're going to have to subtract them like this. You're going to have to do r to the power of 7 minus 3, which is then r to the 4th power. But because we're trying to find r on its own, we're going to have to simplify this, which means we're going to have to try to take away the power like this. Now we're going to have to try to put it into our calculator. So how do we find r? You're going to press alpha window. Alpha window. You're going to press 6, because that's how you put in your own numbers. And then 4. And then you're going to put 12.25, because that's the number you're putting in to the root. And then you get 1.870828693. So you got r equals 1.870828693. So that is your r. But now how are we going to find the AO? So now you will be putting this r into one of the equations. You're either going to put it into day 8 or day 4. I'm going to put it into day 8, and we'll see how it turns out. So for day 8, you have 49,000 equals AO r power 7. So because we already found our r, what would it be to the power 7? So we can just grab it from the top and then put it to the power 7 in our calculator. And that would be 80.21178,011. So let's put that in. 49,000 equals, and that would be 80.21178,011. Now, because we're trying to find this on its own, we're going to have to isolate it. So we're going to divide this from both sides. So that cancels this out. And then we'll divide it over here. So what is 49,000 divided by 80.21178,011? So let's put in 49,000, my calculator, divided by 80.21. And then you get 610.8828396. And there you have it. You have your A. Now, we're still not done because we still have to try to find day 6. We are going to find day 6 by using the same geometric formula, and it's going to be a lot easier this time because now we have found our hidden variables. So n equals 6, and then you have your AO, which is 610.882.8396. And then you have your R, which is 1.8708286993. And because you have this, because your n equals 6, you're going to do 6 minus 1, which is then 5. Now, let's put this into our calculator. Okay, so yeah, 610. Let's put parentheses, oops. And then you put the 610 over here. And then you put 1.870 over there to the power of 5. Then you get 14,000.00001, which is basically 14,000. Which is one of the options you have in the problem. So it would be C. That is how you get your answer. The table gives the amount of fusants in millions on a certain farm at time t years. If the amount of fusants grows exponentially, what would the amount of fusants be at t equals 10.5? So your time, which is basically your x, or your inputs, are displayed over here, as well as your amount of fusants, which is going to be on your y-axis, which are your outputs. So let's put these into a table on our calculator. So let's go to stats. And you're gonna press edit. So right over here, I already have our inputs and outputs on there. Our inputs, we're gonna put them on L1, which is 1, 2, 3. And then our outputs are going to be on L2, which is 138, 158.7, and then 182.51. I'm sorry, 505. Now, because they said this is going to grow exponentially, we're going to have to try to find the exponential growth on this. Okay? So on the calculator, we're going to have to go back to stats. Then we're going to go on calc. We're going to go down until we see exponential regressions. Press 0 or enter. And then we're going to put... And this is going to create an equation for these inputs and outputs. So we're going to press alpha trace, and then we're going to press Y1. That way it can be shown on the graph. We're going to press calculate, and there you have it. So there you have your equation. And because we also want to get our stat plots onto the graph as well, we're going to second Y. Enter. Make sure that they're using the L1 and L2, or at least the columns that you use to put in your inputs and outputs. Then you press graph. See? Those are the plots that you put in, the exact ones, and then the blue line, that's the line that they use with the formula from the stat plots. Now, because we're trying to find 10.5, let's press trace. Remember when you're going on trace, use the one with the line because that spreads out everywhere. Then you're going to put in 10.5. When you put in 10.5, it comes out as 520.60528. And then on the worksheet, it will show as 520.605. It's rounded to the third decimal. And there you have your answer. It's just simple putting in the stat plots and then trying to find the formula. And then you put in your 10.5, and that's how you find your answer. Two function models, f and g, are constructed to represent the amount of merchandise available within a specific grocery store. Both f of t and g of t represent the amounts of available merchandise in thousands of units after t weeks for t is greater than or equal to 0. If f of t equals t plus 3 log base 2 of x and g of t equals t minus 16, what is the first time that sales predicted by the logarithmic model, which is f of t, will be 17.6 thousand units more than sales predicted by the linear model, which is g of t. So right now you have your f of t equation and g of t equation, but it's also telling us that there is a 17.6 thousand unit increase or more than the sales predicted by the linear model. So that means we're going to have to add 17.6 to this equation. And 17.6, when you add it to this, and you add it to t minus 16, it'll equal t plus 1.6. So now you have f of t and your new g of t. So now it's also asking, what is the first time that sales predicted by the logarithmic model will be at that same point? Where will it intersect? So that's where you're going to have to use your graphing calculator. So you're going to press y equals right over here in order to get to this setting. You're going to go to y1 and you're going to put in your f of t. So your f of t is 2 plus 3 log base 2 of x. But because some people don't know how to do the log base, I'll show you. So you're going to press alpha, which is right over here. And press window, which is at the top. And then you can either go down or press 5, because that's where your log base is at. So let's go down to 5, or your log base. And see, it has a little square at the bottom. That's going to be your base. And over here, your base is 2. And inside the parentheses, it is x. And you press x over here, which is your variable. Now for your g of t, because again, you're looking for an intersection, it's t plus 1.6. You're going to put in x plus 1.6. It doesn't matter if the variables change. It's still the same thing. Right now, again, you're just looking for an intersection between these two models. So let's graph it. So the blue one is your logarithmic model, which is f of t, and your red one is your linear model, which is g of t. You can sort of tell which one is which. And now you are going to look for an intersection. So let's press second, trace. And right now you have all these options. You can either press 5 or just go down. And now you have your intersect. So right now, this is your first curve. And now you have your second curve. You're going to put the second curve on the other model. And see, now you have an intersection. Your intersection is at x equals 1.2041903, which is one of the options over here. It's rounded to the third decimal, which is t equals 1.204. That is the correct answer. T equals 1.204. The function f and g are given by f of x equals 3 over e to the power of negative 3x plus 1, and g of x equals 2 over log base 2 of 0.4x squared plus 1, all of that squared plus 1. So let's determine the end behavior of f as input values of x increase without bound. So we have to express the answer by using mathematical notation of a limit. So if it's increasing without bound, we will write it as. So this shows that x is increasing without bound, and put as over we'll put positive infinity as our input. And usually when things are So this is going to be positive infinity times negative 3. So it's going to be negative infinity. Okay? And usually when e goes to the power of negative infinity, it comes out as 0. You'll see that on your calculator if you try to use negative numbers as examples. So at that point, you would just have if e to negative infinity is 0, then you just have 0 plus 1, which equals 3 over 1, which then equals 3. So it's all about plugging and chugging. So at that point, you would say as x increases without bound, the function f of x equals 3. The function g is given by g of x equals 2 all over log base 2 of 0.4x squared plus 1, all of that squared plus 1. So let's determine the end behavior of g as input values of x decrease without bound. And we are going to express it using mathematical notation of a limit. So the first thing that we're going to do is put in the limit. And remember, it's decreasing without bound. So you're going to put it as negative infinity. And then you're going to put the equation, but with negative infinity as your input. So you're going to put 0.4. And then you're going to put your negative infinity squared plus 1. And then you're going to do all of that. Sorry, let me put the line a little bigger. And then you're going to put that squared, and then you're going to add 1 to that. So far that is your that is your equation and with the limit. So let's figure it out. So negative infinity squared is positive infinity. So we get that. So let's put 2 all over log base of 2 0.4 times infinity plus 1, all that squared plus 1. So that is the more simplified version. And then eventually 0.4 times infinity is just infinity. So then you get 2, let's put the limit again. That way, because you're always put your limits, okay? Even when you're done answering the problem. So it'd be log, so 2, infinity plus 1, squared plus 1. There you have it. So now you have 2 all over log base of 2 of infinity plus 1, all of that squared plus 1. Now, infinity plus 1 is infinity. So you're going to do it again. You're going to do 2 log base of 2 infinity, all of that squared plus 1. There. So log base of 2 of infinity squared is infinity. So then you're going to have 2 over infinity plus 1. Which is then, again, 2 over infinity. But because infinity keeps getting bigger and bigger and bigger and 2 just stays the same, at that point it's going to be a number so small that it's basically just 0. So you're going to put it as 0. So you would write out that as the inputs of x decreases without bound of 2 log base of 2 0.4x squared plus 1, all of that squared plus 1, x equals 3. X equals 0. Oh my god. X equals 0. So there you have it. That's your answer. All right, again, it's just plugging and chugging and knowing how to work it with the infinity symbols. The functions f and g are given by f of x equals 3 over e to the power of negative 3x plus 1, and g of x equals 2 over log base of 2 of 0.4x squared plus 1, all of that squared plus 1. So now we are going to determine all values of x for which f of x is greater than or equal to g of x. So how do we do that? So if we're going to determine all values of x for which f of x is greater than or equal to g of x, it's asking when is it going to cut through the x-axis. So when exactly will it cut through the x-axis? Let's do it by putting all of this on one side. So we're going to do f of x minus g of x is greater than or equal to 0. That way we know when both of them will pass through the x-axis. So let's put in the equations. So that way we know how it will be set up. So f of x is 3 over e to the power of negative 3x plus 1. And if we're subtracting gx, it would be 2 over log base 2 of 0.4 x squared plus 1. All of it squared and plus 1. So that's how you would write it out. And now let's graph it onto a calculator. So grab your calculator. You're going to press y equals in order to get to this setting. And then you're going to put in the equation that we set out. Again, we're trying to figure out when it's going to cut through the x-axis line. So let's put it in. Hopefully you wrote it down. So you're going to put alpha y equals 1 because you're trying to put in a fraction for f of x. So you're going to put in 3 at the top. Then to get your e, you're going to press second and see where the e is. It's right over here, but where ln is. You're going to press second ln, which gives you your e. Then you're going to put in the power, which is negative. This is always a negative, okay? Not this one. This is subtraction. This is negative. This is negative, and then you're going to put in 3x, and then you are going to add 1. And now you're also subtracting g of x, so that's subtracting all of this. So you're going to do it again. Alpha y equals 1, because you're trying to put it as a fraction. Hopefully you can see it. And then you're going to put in 2. Then you're going to put in parentheses, because you're going to square this logarithmic function. And you're going to put in alpha, window, 5, because it says 5 by log base. You're doing log base because you have the base of 2. So you're going to put in 2 as your base. And then you're going to put in what's inside these parentheses, which is 0.4 x squared plus 1. Then you're going to do squared again. Oh, wait, sorry, no. My apologies, I accidentally forgot. You're supposed to put parentheses as well because you're squaring the entire thing. So squared. And then you're going to do plus 1 because plus 1 is outside the parentheses. And now let's graph it. Okay, there's your line. And now the last step is to find out where it cuts through the x-axis. So it cuts through the x-axis right over here, but how do we find the exact number? We are going to do second trace. And here you're going to see where it says 0. So you're going to press 2, or you can just go down and then press enter. So let's go, since we can kind of see where it cuts through, we're going to go a little farther away from it. So this is the first line where it surrounds it on the left side, and then we're going to go on the right side of it, and then it'll give us the exact number. Okay, there you have it. So it cuts through the x-axis at x equals 0.2301356. But of course, we are going to round it to the third decimal. So you're going to write out your answer like this. So this is where you have your exact stop. Then you're going to plot the positive infinity, as you can tell. And there, you have your answer. Or this is where you stopped. This is where it cuts through. And that was the point of determining all values of x for which f of x is greater than or equal to g of x. An ecologist began studying a certain type of plant species in a wetlands area in 2013. In 2015, t equals 2, there were 59 plants. In 2021, which is t equals 8, there were 118 plants. The number of plants of this species can be modeled by the function p, given by p of t equals a times b to the power of t, where p of t is the number of plants during year t, and t is the number of years since 2013. Here is the explanation if you need to see it. And now it's asking us to find the values for a and b as decimal approximations. So the first thing we should be doing is, since this is clearly since we have the model over here as function p of t, we can put the inputs and outputs we already have into it. That way we can try to find the values for a and b as decimal approximations. Okay, so for the first one, for 2015, t equals 2 and p of t equals 59. So we're going to put 59 equals a times b power of 2, which is this is contingent on the model for the p model. The next one is from 2021. We're going to use 118 equals a times b to the power of 8. And there you have it. Those are the, with the inputs and outputs, those are the equations that we can use to find the values for a and b. The next thing we'll be doing is dividing them. So if you divide them, the next thing that's going to happen is you're going to divide 59 by 118 and AB squared over AB to the power of 8. So what's 59 divided by 118? Let's check on our calculators. It's actually a simple number, but we'll check it anyways. 59 divided by 118 is 0.5. So 0.5 or a half. So that's your first number. And another thing is that since there's only one a over here and one a over here, one a on top and one a on the bottom, they will cancel each other out. So now you don't have an a anymore. But look at the b's. Because b squared is on the top and b to the power 8 is on the bottom, they have different powers. And when you're dividing them, you subtract the powers. Clearly, there's a greater number of powers on the bottom than there is on the top. So this would be shown as b to the, this would be 1 over b to the power of 6. So how would you do this? How would you try to find b to the power of x to the power of 6? So you're trying to isolate b to the power 6 in order to find it. So why don't we multiply b to the power 6 on both sides? And then you get 0.5 or a half. You can write it either way. Equals 1. Now you have b to the power of 6. 0.5 times b to the power 6 equals 1. Again, let's try to isolate b. So you have b to the power 6. Oh, sorry. Actually, let me try to show you. You divide by 0.5. Divide by 0.5. We have b to the power 6 equals 0.5. Sorry, 1 over 0.5. And because this can also be shown as a half, 1 over 2, you can also write it as this. Which is also equivalent to b to the power 6 equals 2. Now, let's try to get rid of the power. So I'm going to do this. And we're going to do the same thing to 2 on that side. Now let's put that into our calculators. Let's grab alpha, window, and C. You can press 6. And then you put in 6 over here, and then 2, which is exactly what we have in our problem on the board. Then you have 1.122462048. Therefore, B, you can round it to the third decimal. Therefore, it is 1.122. Now that we found our B, the next thing we should be doing is to try to find the A. So we can put our B, but when we try to put our B into one of these, either into 59 or 118, but we have to use the exact one we have in our calculator instead of the rounded version in order to get an exact number. So let's use 59 equals AB squared. So 59 equals AB squared, which can also be written as 59 equals A 1.122 squared. Again, use the one in your calculated version, not the rounded version. So let's put that into our calculator. What is 1.122 in our squared in our calculator? You can go up and then press enter, and it'll show up the exact same way. And then press squared. And that will show up as 1.259921049. So once you have that, you can write that as A times 1.259921049. And now we're trying to find A, so let's isolate A. So you're going to divide that on both sides. So that will cancel each other out, and then you're also going to divide it by 59. So then what does A equal? What would A equal? So then you're going to do 59 divided by that. So let's type in 59 divided by, and again, you can just go up and then put in the same equation, and then it'll come out just like that. So then you get your answer as A equals 46.82833.107, or as your rounded version, 828. And now you have your A and B as decimal approximations. Remember, while you're doing the equation, you want to use the exact calculated version, but once you get your exact values for A and B, that's when you can round it to the third decimal as decimal approximations, since that's what it's asking for. And that's how you get it. An ecologist began studying a certain type of plant species in a wetlands area in 2013. In 2015, t equals 2, there were 59 plants. In 2021, t equals 8, there were 818 plants. The number of plants of the species can be modeled by the function p, given by p of t equals ab to the power of t, where p of t is the number of plants during year t, and t is the number of years since 2013. Here is the problem if you need to see it. And right now we're trying to use an average rate of change to estimate the number of plants for t equals 10 years. So in order to find t equals 10 years, let's first look at the average rate of change. So the average rate of change is 9.833. Now we can put this into y equals mx plus b, which can be used to help find estimates in this problem. Okay, so right now we already know our average rate of change or our slope. So we already know our m. Now we can try to find our b with one of these two inputs and outputs. So let's try 59 since it seems like a smaller number, and t equals 2 seems like a smaller number as well. So let's do 59 equals 9.833 times 2 plus b. Let's put that into our calculator, but again, use this exact version in order to get an accurate number. So let's turn our calculators on. Okay, let's do it. 9.83333 times 2 is 19.666666667. So that's what you would have over here. Now, in order to isolate the b, you have to subtract this on both sides. So what is 59 minus 19.6666667? Now you have 39.333333. So that will be your b. So let's, just to make sure you guys know what I'm doing. Remember, you're subtracting this on both sides. So same thing over here. You subtract on both sides. Then you get 39.333. But you can round it to the third decimal. So that will be your b. But again, use the exact calculated version from the calculator. So now that we found our b, we can now we can successfully attempt to try to find the number of plants for t equals 10 years. Okay, so we already have our b, and we already have our average rate of change. Let's do this. And now we have y equals 9.8333x plus 39.333. So our x is 10. So we put y equals 9.833 times 10 plus 39.333. So let's put that into our calculator. Sorry. 9.8333333. Let's make sure it's the same amount of threes. Times 10 plus 39.3333333 equals 137.666667. So you could round that to 137.667 has a decimal approximation. You're going to round it to the third decimal, and there, that's your answer. That's what it is at t equals 10 years. So that's how you find it. The question is asking us, in which t value, t equals 6 years or t equals 20 years, should the ecologists have more confidence when using the model P? Give a reason for your answer in the context of the problem. I believe it would be t equals 6 years because it's a smaller amount of data, which is more controlled instead of a larger larger population that is a lot harder to control and to calculate. Therefore, t equals 6 years would be more appropriate to use when using the model P. The functions g and h are given by g of x equals log base 4 of 2x and h of x equals e power of x to the power 5 over e to the power 1/4. So how do we solve g of x equals 3 for values of x in the domain of g? So we would equate this, g of x, to 3. We equate it to log base 4 of 2x. The next thing I would do is to try to cancel out the log. So I would do that by putting 4 over here, which cancels this 4 out, and then put 4 over here. So then we'll leave it as 4 to the power 3 equals 2x. Now what's 4 to the power 3? 4 to the power 3 is 64. So you have 64 equals 2x. Now we're trying to isolate x. So we're going to divide by 2 on both sides. And then x would equal 32. That's how you solve it. The functions g and h are given by g of x equals log base 4 2x and h of x equals e to the power of x to the power 5 all over e to the power of 1/4. So how do we solve h of x equals e to the power of half for values of x in the domain of h? So the first thing that we're going to do is equate h of x to e to the power of half. So it would be e to the power of half equals ex to the power of 5 e to the power of 1/4. Okay, there you have it. Now that we have equated it, we will try to subtract these two powers. First, let's simplify this before we do anything else. So then this would turn into e to the power of half equals e5x, because you're multiplying these two powers, over e to the 4th. And because these two have the same base, we can subtract the powers. So that would be e to the power of half equals e to the power of 5x minus 1/4. And because these two are the same base now, we can drop e and just leave it with the powers, which is a half equals 5x minus 1/4. We can add it to both sides, because we're trying to isolate the x in order to find it. So half plus 1/4 is 3 over 4. And now the last final thing to do is, again, isolate the x, and the only thing with the x is 5. So let's divide by it. And then we can divide with this too. So 3 over 4 divided by 5 which equals x is basically saying 3 over 4 times 1 over 5, because you're doing keep, change, flip, which is then 3 over 20 equals x. And that's how you solve the problem.